Get your math on.
Get your math on. Get your math on.
Get your math on. Get your math on. Get your math on. Yes, go ahead. You got the math, doctor. Yes, greetings, greetings. Hey, Mr. Stein. Okay. You're a fashion designer and you have some problems that you need help with math. All right, let's see what we can do for you. Let me hear the problem and see what you need. Okay, you say you're trying to design a hat. You have the design on your computer, all right? I'm drawing a hat design, and you say on the computer that the height of the hat is about 2 centimeters, and the width of the hat is about 4 centimeters. Okay, I'm drawing it just to get a picture of what you're talking about. And then you're going to make a size medium hat, an actual one. Of course, that's going to be a lot bigger than the one that you have on the computer screen. And you're trying to find out if a medium size is 6 times, okay, 6 times larger than the one on the screen. What will your new actual dimensions be? Okay, so I'm drawing that. So you want to know the new height. We'll put a question mark there. And you want to know the new width for the actual hat that will be 6 times the one on your computer screen. All right. Okay. How long you been in fashion design? Oh, 5 years. Awesome. Awesome. So you are probably familiar with a certain concept in geometry that this relates to, huh? Not really, huh? That's why you called me. Okay. All right. Wait a minute. Hold on. I got another call. Hold on 1 second. Yes, you got the math, Dr. Peace. Hey, this is Sabrina Jones. Yes, and you're a video game designer. Go ahead, man. That's awesome. Video game designer. Do you know how much math is involved in video game? Oh, that's why you called me, because you know. Okay, very good. Do you have a problem that you want to be get some help with? Okay, go ahead, explain the problem. So you're designing a new video game, okay, using AI. Got you. Oh, so you're going to have a skier chasing another skier coming down Mount Everest. Cool. And you're taking the actual image of Mount Everest, which is about 29,141 feet high in real terms, in real life. So you're taking the actual image of the Mount Everest and you're going to shrink it down for the video game, for the artificial intelligence, for the AI. You're going to shrink it down to 0.0001 times its normal size. Oh my goodness. And so you want to know how tall it will be on the actual computer screen in the AI. That's what you want. Awesome. Hold on 1 second. I had the fashion designer on the line. Hold on. Yeah, Mr. Stein, I'm gonna have to call you back. I got a video game designer that's asking about a similar question to yours. So let me deal with her and I'll call you right back afterwards. All right? Okay, hold on. Yeah. How are you doing? Yeah, this is Math Doctor again. Yes, this is our video game designer. So I'm looking at that. This a real simple task. All you need is a certain geometrical term. Yeah. Oh, wait, hold on. I got another call. Hold on 1 second. Yes, you got the math, doctor. This is Belinda Jones. Okay. And you're a farmer in Arkansas. Man, that's awesome. I love farming. I got a little small farm myself. Yeah, my wife and I. In Michigan. Awesome. So what's your question for the math doctor? Okay. You have a garden in the shape of a rectangle, and the dimensions are 5 feet by 8 feet. Okay, nice little garden, you know what I mean? You know what I mean? Probably got some tomatoes in there, right? Right? Got some tomatoes in there, okay. Got some yellow squash in there, you know what I mean? Some yellow squash, okay, okay, great, great, great. What else you have in there? Heads of lettuce. Oh, heads of lettuce. I'm drawing some lettuce in there right now. Okay, so what's your question? All right, so when you did this raised bed 5 by 8, you said you used 9 bags of organic soil. 9 bags of organic soil, okay. And then what are you trying to do? You're going to build another raised bed that's a lot bigger than this one, okay? Still a rectangle size? I mean shape, okay, still a rectangle. And it's going to be what again? 3 times as large. Width and length. 3 times your other older raised bed garden. Okay. And you want to know how many bags of soil and what your new dimensions are, length and width. You called the right person, a math doctor, but hold on. I got the video game designer still on. I got to let them know I'll call her back. Yeah, video game designer. I got a farmer on. He has a problem. I just talked to a fashion designer. They have a problem. All of you have a similar problem. Guess what you all need? Bam! You need to get your math on. That's what they needed to do. They need the math doctor. Hey, I'm here, Shahid Muhammad, the math doctor. We're back. It's time to what? Get your math on. That is right. The fashion designer, the video game designer, the farmer, and so many other professionals needed a certain geometrical term, a certain geometry concept to help them solve the problem. And guess what it is? Let me hear you say it. Yes, it is similarity. Ding, ding, ding. They needed to know similarity, use similarity in order to solve their problems. So what I'm going to do is give you a brief, short lesson on what similarity is and how you can use it to solve problems similar to the fashion designer, similar to the video game designer, and similar to the farmer and so many other people, photographers, architects, engineers, people that make small toys and make them into larger toys, people that make souvenirs. The list goes on and on and on. All of them have to get their math on. So let's go to the math doctor. Hey, that's me. And we're going to look at a brief lesson on this concept of similarity. Here we go. We're on. Take it away, math doctor, me, myself. But I got a nice bow tie on. Here we go.
Special, similar concept, but a little different. And then you'll find that what I just said, when I said similar but different, actually has a lot to do with today's lesson, all right? So let's go to the PowerPoint so you can see some visuals. Now, if you notice, look here, you will see 2 stealth bombers. These are 2 exotically fast, sophisticated military aircraft called stealth bombers. What do you notice about them? You may shout out and let me hear you. Yes, I heard one of you say that they have the same shape. They look exactly the same, but they have a what? Different size. Absolutely. That means they cannot be congruent, because congruent means same shape, same size. These must be some other type of geometrical concept that we're going to talk about in a few seconds. All right. So notice these 2 stealth bombers have same shape, but different size. Now, if you go to India, there's this famous place called Taj Mahal, and you see it down on the right here. That is the actual picture of the Taj Mahal. But the upper left picture is a model that someone constructed of the Taj Mahal. But the shapes are the same, pretty much, right? Not exactly the same, but they made a good attempt. But the size is what? Different. I don't know how many of you have ever gone to a museum, gone to a famous monument, and went to the souvenir shop and got a small model of the big monument. So if you go to the Washington Monument, you can leave with a little small Washington Monument, a smaller version of the same thing. If you come here to Chicago, where I am, and go to the Willis Tower, in the souvenir shop, there's a small version of the Willis Tower that you can take home for yourself, all right? If you go to the pyramids in Egypt, you can get little pyramids that look like the great big ones, but they have a what? Different shape. This is an example of that, actual versus model. Some of you play with little cars, those model cars, all right? They look just like the regular cars, but they're what? Same shape, different size. Some of you play with doll houses. The doll houses have furniture just like in your house or someone else's house, but what? Same shape, different size. That couch that is in your doll house, you cannot sit on or you will crush it and break it, okay? But that couch may be similar or have the same shape and size as another one. I kind of gave the word away. I wasn't supposed to do that yet. All right, next. Look at these two Ferraris. Good Lord, the math doctor wishes the big one was his. But you have a big Ferrari, and then you have a model Ferrari, a smaller one. But everything is the same. Shapes are all the same. All the angles are the same. All the sides are the same. The only difference is in what? Size. So the larger actual Ferrari is bigger than the model Ferrari. These all, family, belong to a certain geometrical concept called similarity. Give it up, give it up. Yes. Similarity is when objects or figures have different size, but same shape. So all the examples I've given to you so far had different sizes, same shapes, all right? Similarity is used in so many different things. Some of you might have gotten a class picture before. When you get class pictures, you can get a wallet size, small version of you. You can get maybe a 6x9 version of you, and you could even get a big poster size of you. Those are all similar photographs. If you design or want to go into fashion design and you want to design sweatsuits, you want to design gym shoes, on the computer will be one size, but when you actually make it or manufacture it, it will be a different size. But it's same shape, different size. They will be similar gym shoes, dresses, sweatpants, caps, whatever you plan to do for your fashion design, all right? Similarity is in so many different places. Architects, any of you want to be an architect, an engineer, you're going to be dealing with similar things. When a person designs a new car, they design it maybe on a tablet, maybe on a computer, and then that bad boy is made, manufactured into a much or larger size. Those are similar figures and shapes. Let's look at some more. If you look at this diagram, we had this on the last video lesson the math doctor gave you, and we were looking at congruent. And I asked you which shapes are congruent. And the only ones that you said there were the red triangles. But the other shapes are not congruent. They are what we're talking about now, similar. So the blue pentagon is similar to the other blue pentagon. Same shape, pentagon, different size. The green rhombus or diamond is similar to the other green rhombus or diamond on the right of it. Same shape, a rhombus, different size. The green, light green rectangle is similar to the other rectangle that's green. Same shape, rectangle, different size. So when things are similar, the one is similar to will be of a certain scale to the original one. It may shrink in size or it may blow up in size. All right. Look at these two little coyotes, wolves, whatever they are. They're cute. All right. But you notice that the one on the right, my right, is bigger than the one on the left, but everything else is the same. They have the same shape, the same smile, the same nose, the same tail, but they differ in size. These two wolves or coyotes are similar in shape. Look at these two dogs right here. These dogs are similar. One on the right is bigger than the one on the left. However, they have the same shape. Tails are the same, arms folded the same, angles of the ears are the same, but the size is blown up on the right and shrinked on the one on the left. Or the one on the left has been shrinked. Look at these butterflies. They are exactly the same in shape, in form. However, they differ in size. These butterflies are similar to one another. There's a certain scale or number that one was blown up or multiplied by, or the other one was divided by to make it smaller. Okay? You'll deal with the scale factors later on when you get into your middle school similarity discussion. Now, these are two examples of similar triangles. I want you to look at two things, their angles and their sides. If you notice, their angles are all equal. When you see these little arcs, this is for higher math, but hey, you're there now. You're smart math guys. It means that they are equal, all right? So, hold on one second. So those angles are equal, but notice their sides. The sides are in different proportion. This one is 10 and this one is 20. That means you multiplied it by 2. This one is 6, where this one is 12. That means you multiplied it by 2. And this one is 7 and this one is 14. That means you multiplied it by 2 as well. Okay? So when things are of the same size or shape, they also differ in the size of the sides. So we have similar figures have the following attributes. Their angles will all be equal and, make sure you're looking at the right thing. There we go. The angles will all be equal in similar figures, and their sides will be blown up the same amount. So notice the side 10 was blown up by 2, making it become 20. The side BC was blown up by 2, making it go from 6 to 12. And the side AC was blown up by 2, making it go from 7 to 14. All the sides must be blown up the same amount or divided by the same amount in order for the shape to stay the same. If you would have blew the 10 side up by 3 and blew the 7 up by 2, the triangle would be distorted. It would not look like the other one, all right? So when two shapes are similar, they will have all angles the same, but the sides will be proportional. That means the sides will be blown up by the same number times or divided and shrunk by the same number through division. Look at this one here, these two here. You clearly see the angles are all the same, right? And look at the side, blown up by 2 again. 4 blew up to 8 times 2. 1 blew up to 2 times 2. 5 blew up to 10 times 2. And 6 blew up to 12 times 2. So all the sides were blown up the same amount. We call that the scale factor. This has a scale factor of 2, all right? Every side was double. Look at these bats. Some of y'all like Batman, all right? The bats are similar in shape. They have the same angles. The sides are blown up by the same amount, making the smaller bat similar to the larger. So we discussed in the last video lesson congruence. And in this video, we're looking at similarity. And we clearly see that similar means same shape, different size. Congruent means same shape, same size. That's why the congruent symbol has an equal to sign in it. But look at the similar symbol, no equal to sign. Because they're not equal, they only have the same shape, but not the same size. So we thank you for watching this quick video lesson on similarity. I'm going to make sure I put a nice video from YouTube that I saw and I like for you also to check out. I'm going to try to get you a math game as well as your regular quiz, okay? So until next time, well, the next time hopefully will be when you take the next course, which is the 4th through high school basic essentials as you elevate and graduate into your next grades. Take care, be safe, and make sure you get your math on.
Math doctor, that's what I'm talking about. Similarity is what we're talking about. And in all the problems that we had from the calls that I got, it all deals with what is called scale factor. So the farmer needed to know the scale factor. And the scale factor is how does one side correspond to the other side? So if he wanted to be as 3 times as large as the original raised bed garden, then that means 5 times 3 would be 15. So the length would have to be 15 feet and the width would have to be 8 times 3 or 24 feet. And that means the scale factor is 5 to 15, which is 1 to 3. That's for the length. And the scale factor for the width has to be the same, 8 to 24, which is 1/3. So the scale factor would be 1 to 3, and that makes sense because he's blowing it up, making it larger 3 times its original. The same with the fashion designer, the same with the video game designer. All you have to know to solve similar problems is what is called the scale factor, what one side is to the other. With similarity, you always have a smaller shape and a larger shape. So you can go small to large with your scale factor or large to small. It all will be the same depending upon what you do for your numerator and your denominator for your scale factor. All right, I hope you see the importance, the relevance, how critical it is to get your math on to solve very critical problems. Until next time, fight the power, do the right thing, and what do we always say? Get your math on. Take care. Until the next episode, we'll see you. Peace. Get your math on.
Get your math on. Get your math on.
Get your math on. Get your math on. Get your math on.